Alright, so now you've tried one problem on your own. We're going to talk through another example. This was a little trickier, and then you're going to give another one a try. So just as a note, this example 4 we're going to skip. It's similar to one of the other ones that we were doing. But we're going to do example 5, which is a little trickier like I had already mentioned. So as we read through this problem, it says 0.5 liters of hydrogen gas are reacted with 0.6 liters of oxygen gas at STP. What volume of water will you produce at 1 atmosphere and 350 degrees Celsius? Now this is the balanced reaction for this reaction. You're going to have to make sure you can balance reactions still. Actually, this is missing a 2 here, so make sure you add a 2 here in your notes. Then we've got 4 hydrogens on either side, 2 oxygens, and 2 oxygens. Okay, so add that 2 in here for me, please. Thank you. Alright, so as we go through this problem and we kind of think about how we're going to start it out, you're going to see a lot of stuff from stoichiometry is going to come back to play here. So we first have these 2 different amounts. So we've got 0.5 liters of hydrogen gas and 0.6 liters of oxygen gas. That means we have an amount of this reactant and another amount of this reactant. Whenever you see those 2 amounts of the reactants there, one for each reactant, that's going to clue you in that this is one of those limiting reagent problems that we talked about a long time ago. Remember, we did the s'mores activity talking about what a limiting reagent is. So that means the first thing you're going to have to do are some bridges to figure out which one of those 2 is it going to run out of first, and that's going to ultimately determine how much you're going to use for the rest of the problem. So that means we're going to take each amount here. So we've got the 0.5 liters. 0.5 liters, and that is of H2. Going to put that in a bridge, and then we're going to put the 0.6 liters O2 in another bridge. Okay, now we need to ultimately figure out how many moles of product each of those could form. So we're starting out in liters of each reactant. We got to get to moles of water for each of them. Okay, remember you compare the amounts of the product. The one that forms the lower amount is going to be the one that's going to run out of first, and that's ultimately going to determine how much you can make. Remember, the reaction can't go on unless you have both reactants present. So we have these 2 values here, 2 different bridges. Now, what you might not remember from back when we did these problems, liters comes down here, which is normal. But the thing that you kind of have to pull back in our memory here is that 22.4 liters is the number of liters a gas takes up at STP for a mole of gas. So we're going to put that 22.4. You might remember that's the only number we ever put in front of liters. And like I said, 1 mole of H2 or 1 mole of O2, doesn't matter what the gas is going to occupy 22.4 liters when you're at STP. So both of those are going to have that 22.4 number there. Now we're in moles of our reactants. We got to get to moles of our product. Here's where you're going to use the balanced reaction to figure out what numbers go next. Remember, whatever we see up here has to come down, so moles of O2 here. We got to put moles of H2 here. We're trying to get to moles of product in both cases, so I'm going to write mole of H2O in both cases there. Now, in front of these, this is that mole ratio step, you use the coefficients from the reaction here. So 2, 1, 2, once you add that in there, are going to be the numbers we're going to use. So we have, if we look in front of the oxygen there, there's a 1, so we're going to put a 1 here. In front of the water, there's a 2, when you added that in there, and then there's a 2 in front of the hydrogen. Okay? At this point, we are in moles of H2. You can check these out that they cancel as you go. Okay, we're in moles of water, which is what we want. So we're going to go ahead and calculate these. So if you calculate that first and multiply by across the top, divide by what's on the bottom, you're going to get 0.022 moles of H2O here. Then on the bottom, you're going to get 0.054 moles of H2O. So you look at these 2 numbers here, the 0.022 and the 0.054, and you figure out which of the two is smaller. That's going to be the limiting reagent, which means that's how much we can make until we run out of it. So 0.022, 0.054, that means this one's smaller. Okay? So that's going to be the amount we're going to use. Now, take note that's already in moles, so that's going to turn into our value for N. Okay? So now that you have both of these two written down, we determined that's our N value here. I'm going to go ahead and erase the other one because that one doesn't matter to us anymore. So, steps that came back from stoichiometry. The bridges, units coming down, the 22.4 liters for 1 mole, and this mole ratio step is huge. So make sure you remember how to do that one. All right, now, next step we have N. Okay, so I'm going to start writing down the other numbers we have from the problem. So we have STP, meaning that it's made, I should say these are reacted at STP here, so that allowed us to do these conversions. But we want to know what volume of water will be produced if we have 1 atmosphere and 350 degrees Celsius. So that means we need to use those values as P. So 1 atmosphere for P, and then T is going to be 350 degrees Celsius. We got to convert that to Kelvin though. So when you add 273 to that, you're going to get 623 Kelvin. Okay? So now we have N, we've got P, we've got T, we know R, okay? And it asks us what volume, so that's perfect because that's what we have left here. So we're going to use PV equals nRT. We are solving for V. So I'm going to rewrite this equation to solve for V. So V is equal to nRT over P. So I start plugging in some values. So N is 0.022 moles. R is always the same number. T is 623 Kelvin. And then that P value is 1 atmosphere. So that's going to go on the bottom. So 1 ATM down there on the bottom. So if we go ahead and start multiplying our numbers. So 0.022 times 0.08206 number times 623 Kelvin divided by 1, so that doesn't really matter. You're going to ultimately get that we have 1.125 liters. Now the question did ask you what volume of water, so we can write liters of H2O here to clarify. But that's the number we're looking at. Okay? So, key things to keep in mind here. If you haven't already noticed, most of these stoichiometry problems use the ideal gas law. Okay, that's because we're not changing conditions. We want to know something about what we have already. We use stoichiometry in terms of the bridges. These conversions are coming back to 22.4 liters. The mole ratio step is a big one. Once you get that far, that gave us N. At that point, this is what you're used to doing. So plugging in the numbers to the ideal gas law, getting an answer at the end. So that being said, there's number 5 done with you guys. We're going to work on number 6 and see if you can get an answer for that one independently here.